Hello, welcome everyone. It's about time to get started with the next session. I hope you all had a great lunch. Everyone who hasn't joined seating here, let's get seated, and then let's all get a great hand of applause to Nuno Faria for his talk about building Tetris in a SQL query. So let's give him a hand.
Hello everyone, my name is Nuno Faria. I work as a researcher at InescTech, and today I'm going to talk about how can we build the game of Tetris in a single SQL query. But before doing so, let's first take a look at some background information. So starting with common table expressions, or also known as CTEs, they have been into the SQL standard since 1999, so a long time ago, and they allow us to take a subquery and rewrite it as an auxiliary expression, and then refer to it by its name, just like a regular table or view. So in this example here, we create a recursive CTE, a regular CTE using the with keyword, and then we use it in this join here, just like a regular table or view. Now, one feature of these CTEs is that they can also refer to themselves, and this is known as recursive CTEs, which have been into the SQL standard as long as the regular CTEs. And by doing so, they allow us to specify workloads which would otherwise not be possible directly using SQL code. And just as a side note, even though they are called recursive CTEs, in Postgres and many other systems as well, they are evaluated iteratively. So who here has worked with recursive CTEs before? So quite a lot of people. So they will probably recognize this query over here. This is like an hello world when it comes to recursive SQL. So we define our CTE using the recursive keyword. And then when we build a recursive CTE, we always specify the non-recursive term. So this is the first term that will be evaluated in our query. And it will generate the first row or multiple rows. And then we have the recursive term, which contains the which will be evaluated in each iteration. And in this case, we will continuously evaluate this term until the current number of the column I is less than 10. So we generate a sequence of 10 numbers. Now, looking at a slightly more complex example, we have a graph related to a dependency network, and we want to compute the transitive closure of one specific dependency, in this case, the dependency A. So we have a recursive CTE which starts at node A, and each time we execute our recursive CTE, there are three main sets. There is a result set, which will store the rows used by, returned by our recursive CTE. There is a working table, which contains the rows generated in the previous iteration, and also there's the intermediate table, which stores the rows generated in the current iteration. So in each iteration, we take the rows of this intermediate table, and this intermediate table becomes the working table, and the rows are also added to the result set. And so we keep doing this process, and in this iteration here, our intermediate table generates the same row C that we already saw. So because we are using an union over here, it will remove any duplicate rows, and it will also not add them to the working table. And we keep doing this until there's nothing else left to join. So the addition of this relatively simple feature makes SQL a Turing-complete language. So in theory, we can create any algorithm or build any algorithm given enough memory. And this has several actually useful applications, and also less than real-world applications, like building a 3D render or a ray tracer directly in SQL. So why should we use recursive CTEs? So the first and main reason is that it brings our workload closer to the data. So we can execute directly on the database without having to transfer large sets of data to an external application. We can use any existing indexes, so we don't need to create them from scratch. And if our workload requires to process large sets of data, we can use the database's own buffer manager and disk spilling, without having to worry about that. And just a quick comparison between a recursive CTE that computes a transitive closure against a version that uses the procedural language of Postgres, and also an example in Python. When we test the transitive closure using the Rust's crates.io dependency network, we see that the Python version is way more expensive than both the CTE version and also the procedural language in Python. Because while the Python version needs to load the entire data or scanning the entire table, and then build, in this case, a dictionary to process the workload, our recursive CTE can use an index scan and get to the data directly. But before throwing away your Java code and your Python code and rewriting everything into SQL queries, as fun as that would be, there are some limitations with recursive CTEs. And the first one comes precisely to speed. So the previous example, we saw that Python was way slower than using a recursive CTE. In this case, using the CPP dependency. But if we use a dependency that contains more dependents, so it will require more iterations of our CTE, now we can see that the bar for the recursive CTE is starting to increase. And if you use the Postgres dependency, which is really popular, now the differences between the Python version and the CTE version are starting to get close to each other. But still, the CTE is still faster, so no problem here. But what if instead of computing the transitive closure of one dependency, we compute the transitive closure of two dependencies at a time? Now the Python overhead of having to load the data and building the dictionary makes up for the slower iteration speed of our recursive CTE. And if we use even more dependencies, now we can see that the differences are now really starting to increase. The other limitation comes down to the memory growth. So consider this simple recursive CTE, where we generate 10 million rows, but then we are only interested in the last iteration. So we order by, and we do a limit, and we only get, at the end, the last row, which is quite a common use case with recursive CTEs, so generating a lot, or processing a lot of iterations and only getting the last state. If we compare the resource usage in Postgres, MySQL, and also DuckDB, you can see that even though that we are only trying to get the last row, Postgres will store the entire result set either in memory or in temporary files. The same thing with MySQL, but DuckDB is able to optimize this result. On the other hand, you can see that here at the bottom, this is the performance of DuckDB, so that's your trade-off. But I think in theory, Postgres could also optimize this use case. Now, the other limitation is that we can't access the result set in our workload. We can only access the last iteration. And just to show an example of this limitation here, we have here an example which computes the shortest path between one node and all the other nodes in a graph. And when we use this example here, we will start at node A, and then we keep following the paths in order to build the shortest path. And in this iteration here, we reach node D from B, C, and D, and we see that the cost to reach that node is 14, which is more expensive than another path already found to node D from A and D. But because we can't access the result set, we don't know that this path is worse than the other path, so we need to maintain it in memory, and we also need to keep following it until the end of the graph. So we need to store more memory, and we also need to use more CPU resources to compute additional paths. Luckily, there's a solution to both this problem and also the memory problem, and it uses this using key feature. So this feature allows us to define a key in our recursive CTE, and when we generate new rows with the same key, instead of just appending those rows to the result set, we will actually replace the existing rows in the result set that have the same key. And also, it allows us to access the current result set using the recurring table keyword. This feature has been recently presented at SIGMOD, research conference this year, and it also been added to the production build of DuckDB. So over here we have a regular recursive CTE, which computes a factorial, in this case, of 3 and 5. And when we execute this recursive CTE, we start with the first iteration, which generates those first 2 rows. And in the next iterations, we keep adding those rows to the result. So we need to store all of these rows. And then if we want to get just a factorial, we need to filter out and get just the last iteration. But using this using key feature, we can define the column n as being our key, which is this column here. So it's either 3 or 5, so the number that we are trying to compute a factorial. And we just do this modification in our recursive CTE. And now, once again, we generate the initial rows. But in each next iteration, instead of appending those results, since they will match the same key of an existing row, we will update those or the recursive CTE will update those rows. So what we're left with is just the last iteration, so we don't even need to filter out and get those values. And just to show this using key feature in that shortest path example, now when we reach the node D again, we can see that the cost is higher than the previous path, and using this filter here, we can remove that path from the result set. So we don't even store it, and we also don't even follow it until the end. And just to show the impact of this optimization, here we have a comparison between Postgres using a regular recursive CTE and also DuckDB with the using key feature. And when we increase the number of nodes in our shortest path example, both the number of paths that are generated and also the runtime increase exponentially in Postgres, while it only increases linearly in DuckDB. So the other limitation comes down to the parallelism. So CTEs, whether or not they are recursive, are not considered parallel safe. So we cannot have parallel operators over those CTEs. So if we have an example like this, where we generate 1 million rows and then we apply a really, really bad regular expression, and we have an alternative implementation which takes the results of takes the rows of a recursive CTE and creates an analog table, and then applies the regular expression and then deletes the table. This temporary table version becomes five times faster than the recursive CTE only version, because it is able to use a parallel sequential scan, and thus it will be able to use multiple cores. And finally, and this is not really a limitation, it's more a consideration, it comes down to the transactional isolation when executing queries. So each iteration in our recursive CTE will always read from the same snapshot, even if we are using the read committed isolation. So we might have a recursive CTE reading from a table and concurrently have a transaction which is updating that same table, but our recursive CTE will never see any new updates made to that table, even if the other transaction commits and we are using the read committed isolation. And this is probably for the best, so we don't get surprised when running our recursive CTE, but just think of it as foreshadowing for what's to come. So when should we not use recursive CTEs? So maybe it is faster to take our algorithm and implement it externally. So maybe the set of data that we are trying to process is relatively small compared to the number of iterations that we require. Maybe our algorithm just needs to access the result set, and this could be solved with that using key feature, but it's not available in Postgres. So if any Postgres committers are watching, please consider this. Or also, maybe our algorithm is just complex enough to represent in a declarative language like SQL. And if I had to pick an example out of many, I would say definitely the game of Tetris would be such an example. With that said, how can we actually build a game in SQL? So the first thing we need is a game loop, so something that executes, and in each iteration will render the game to the user. And for that, we're going to be using recursive CTEs, and also the PG sleep function, so we can implement a consistent frame rate between or during our game. Now, the next thing we need to handle is the output. So we need to render the game so the user can see what's happening. One problem is that we cannot rely on the CTEs output as our game rendering engine, because at least in the PSQL tool, the output only appears after the CTE finishes, so it cannot be used there. But what we can do instead is use the raise command to print some string to the standard output. And this command is only available in the procedural language of SQL, so we need to create a temporary function just to make it available to regular SQL code. And okay, this is the only piece of procedural language that we need to implement our game. So we implement Tetris in one SQL query and one PSQL function. And we can now take our string, we can add some empty space, and now the result can appear animated on the screen. So the output is done. Now let's take a look at the input. The problem with this is that our query will run server-side, so there's no way to read the actual user keystrokes directly. But what we can do instead is, since we are using a database, we can create a table, in this case called input, which will be used as the communication bus between the user and our game. And in addition to the actual command that we want to execute, there's also a timestamp that we add just to ensure that we don't process the same input multiple times. But we're still not done, because due to that isolation slide that I mentioned earlier, our recursive CTE will never be able to read any new updates made to that table. But what we can do instead is use the dblink extension, which is built in, so it's not cheating. And this extension opens up a new session. It's usually used to open a new session to a remote database. We'll connect to the current one, because that makes sense. And we'll use it to open a new transactional context, and thus be able to read updates made to the input table. So we connect only once at the start, and then in each iteration, we can use that dblink extension to get the result from the input table. But Postgres is smart, and it says no. I'm going to cache those results because the query that you're trying to execute is always the same, so no point in keep executing over and over. So we need to trick Postgres and make the query unique. So we can simply add a comment with the frame number, and the query is unique, and thus no caching is made. Or we can also use or disable these caching operators. And finally, now we can get the recursive CTE to read updates made to that table, so then it can keep processing the game. When it comes to the type of data that we store, there are two types of data. So there is constant data, and this includes parameters like the frame rate, the board dimensions, how many points we score per line, the information about all the pieces in the game in the different rotations, so the initial coordinates of each piece, and also the information about our dblink connection. And all of these are created using regular CTEs at the start of the game. As for variable data, this is the row that is stored in our recursive CTE, and it keeps changing, and includes the frame number, the current board, the current piece, how many lines have we cleared so far, and so on. When it comes to the board encoding, this is done with one-dimensional Boolean arrays. One-dimensional because at least I find them easier to work than 2D in Postgres. And each cell is either true, meaning it is filled, or empty, meaning it is, or false, meaning it is empty. And in addition to the regular game cells, there's always a column here at the end, which is hidden from the user. And this column is always set to true, so there's always blocks there, which makes the collision detection of our piece easier to compute when it moves to the edge. As for the game logic, each iteration will have 3 main steps. So the first one is reading the user input, and this is done with the dblink extension. Then we can process the state, and this is done with subqueries joined with lateral joins. So the lateral joins will allow us to take the result of the previous subquery and use it to compute the next one. And finally, to render the game, we use that notify function that we created. We stop the game when we can drop any more pieces, so we have that filter there which when the piece gets stuck when spawning, it stops the game. And when the game is over, we project only the score at the end. So to implement a movement, this is done with an array which contains information about the current piece. And this includes the ID of the piece that we are playing right now, the ID of the rotation, how many cells we have moved the current piece, so then we can translate the current piece by that amount of cells, and also a flag that says if the piece has moved down, so then it's easier to determine if we are dropping a piece and colliding it with the bottom. So this is just a small part of the tetronymo piece, which contains in this case, the T piece and all the initial positions in all of the rotations. And so here we have the piece at the spawn, so it is at the center and also at the top. And when we move this piece to the right, we simply increment by 1 that the number of cells move. So then we can take the initial piece and translate it by that number. When we move it down, we increment that number by 11, so we move a complete line down. And when we rotate, we simply update that number, so we get the new piece from this tetronymo CTE. The movement itself can be caused either automatically, so the game will continuously drop the piece based on some delta, or also when processing the user input, and this is simply done with a case with different conditions. After the piece has been moved, we need to determine if the move was valid, so we need to determine if there are any collisions. Luckily, since we have SQL, we just take the current piece and we join it with the board, and then we find out if any of the pieces are filled. So if they are filled, it means we have a collision. After we drop a piece, we want it to clear 1 or more lines, and to do so, we take that one-dimensional array and we split it into the different lines, and then again we have SQL. We can filter out the lines which are completely filled, which is relatively simply to do. The other important subquery is the max drop lines subquery, which computes how many lines we can drop the current piece. And this is used to implement the hard drop, so we press space and the piece falls completely, to simulate where the piece is going to fall, so also called the ghost piece, and also to detect if we are at a game over state. And to implement this, we now have another recursive CTE, so now we have recursive CTEs inside recursive CTEs, and this takes the current piece and drops it down line by line until it collides with another piece or another block. We also need to generate new pieces when we drop the current one. To do this, we take a similar approach to the NES Tetris game, so we generate a new piece, and if that piece matches the previous one, we generate another just to remove some bias against generating duplicate pieces. And finally, to actually show the game to the user, we take our entire state and we convert it to a pretty string. So we add the game header at the top, we render the board with the current piece and also the ghost piece, and then to show the string to the user, we call the notify function. And now, just for a quick demo, the entire code is available on GitHub if you want to check it out. One thing I didn't mention is here at the bottom. So there's also a Python script which reads the user inputs and sends the update queries to the input table, which makes it way easier to play than actually change the input by hand. So on the bottom we have that script, and on the top we have the query being executed. And when we execute the query, we can see at the top we have the header, the current score, the next piece. When we get a new piece, we can move it left, right, move it down. We can press space and the piece will fall completely. We can rotate the piece. And what I'm trying to do here is build a small tower, because if you ever play Tetris, you know that the more lines you can clear at once, the more points we get. So I'm trying to get that line piece, which will take a bit. And I should be, right now, there's a line piece. When I drop it, those last 4 lines will be cleared because they are completely full. Fast forward a bit, you can see how bad of a player I am. So some holes are starting to be formed. The level increases, which also makes the things harder because the pieces start to fall at a higher rate. And when I can't drop the piece anymore, the game is over and only the score is projected at the end. So again, if you want to check it out, try it out for yourself. It actually works. So this is true. So you can go and check it out. So that has been it. Thank you so much for being here. There's also a link for the talk feedback if you want to give some. And once again, thank you.
So, thanks for a great talk. That was amazing. I wouldn't suggest anyone running this on a production system. It sounds like a security nightmare. But anyone, any questions? I suppose. No questions? Oh.
It's just a funny question. Do you have any patent on this?
Sorry.
Patent?
Patent? No, you can. I think I would be sued by Nintendo.
Any more questions? If not, then thanks a lot.